Hello everyone, and welcome to Lecture 11. Today we're going to be talking about BGP routing, which is a pretty exciting topic because this finally will clarify some questions about how the internet as a whole is kind of joined together and how we create paths across the entire internet. Last time we talked about two things. So first, a little bit about the internal of routers. There we looked at how there's more than one queue in a router. There are queues on the input ports and output ports, and there's a switching fabric in between the two. We also saw how weighted fair queuing is a way to create different priority classes for packets so that some packets, you spend more time sending certain types of packets if they're higher priority. That's a way of doing differentiated service. And then we moved on to routing algorithms. And the purpose of a routing algorithm, the reason we're studying this, is to determine the forwarding table in each router. So implementing the forwarding tables themselves was the data plane of the network. Now we're moving to the control plane of the network where we're actually deciding those routing algorithms. What we're doing is solving a shortest path problem on a weighted graph that represents the network. So we talked a little bit about that graph representation. And we talked about two different styles of algorithms. One were the centralized or global algorithms. This is like a traditional shortest path problem you might have seen before, where we have full information about the graph and we simply run an algorithm that solves that. For example, Dijkstra's algorithm is a efficient way to solve one of those centralized shortest path algorithms or problems. Excuse me. We call those centralized algorithms link state algorithms because we have all the states of the links in the whole network. And that style of algorithm, it turns out, is used by some protocols that operate within a subsection of the network called an autonomous system. We'll talk more about that today, such as the open shortest path first protocol. And in order to implement that kind of algorithm, you actually have to broadcast local link information to the whole network. We'll talk in the next lecture about how to implement a broadcast to share information about the whole network to the whole network. Okay, but that was a centralized approach to finding the shortest path. Dijkstra's algorithm was. The alternative to that is a distributed approach, and we introduced the distance vector algorithm for solving the shortest path in a distributed way. And with this style of algorithm, we have nodes that only have information about their neighborhood, about the connections they have to their neighbors, and they share information that eventually propagates through the whole network in some form. But no one node ever knows at any given time all the information about the whole network. That's a big difference between a distributed algorithm and a centralized algorithm. And in the third project, you'll implement both a distributed and centralized algorithm for computing shortest path for determining routing. So we'll talk more about distance vector today and see how the border gateway protocol, BGP, is based on distance vectors. And this solves like the high-level routing problem on the internet. So let's get right to it. Last time at the end I went pretty quickly through a distance vector algorithm, and this is important because it's used in BGP, so I'm going to repeat that a little bit and demonstrate it a little bit more clearly. So central to this algorithm are distance vectors, which we abbreviate as DVs. Every node in the network, so the nodes are going to eventually, so far we're approaching this abstractly as a graph, but every node is really a router in the internet, and the edges are links. So every one of these nodes has a distance vector for itself. This distance vector lists the costs and the next hop for every destination. By next hop, I mean where would you send traffic, or I guess in general, if we're talking about a graph, where would you move next if you wanted to get to that destination in shortest possible cost, which is to say, if you're following the shortest path from here for every destination, where do I go next to reach that destination, and what's going to be that final cost when I go through all the hops that will lead to that destination. So again, we only have one piece of information for every destination, only basically the best choice for how to get to that destination from this particular source. And because it's based on this particular source, we have a different distance vector for every node. Every node has a different next hop and different total cost to reach all the other destinations in the network. Technically, I mean, at a lower level, if you're implementing this, you could think of it as a dictionary mapping from destination. That's the key to two things: the cost to reach that destination and the next hop that puts you toward that destination in the along the shortest path. This is not just any next hop that'll lead you to a destination. It's the next hop that has this particular cost, which is the lowest cost to reach that destination. Okay, so that's a distance vector. Hopefully that's fairly clear. But we need to also understand how we use that distance vector and how we generate it in the first place. Okay. When we have this, of course, we can use it for routing. The next hop tells you which direction to travel to reach the final destination. I said that already. And so if you're traveling from any source to any destination, as you travel, you just, whatever location you're currently in, whatever node you're currently at, you check that node's distance vector to get the next hop that tells you where to go next. So by checking the distance vectors as you move along, you can figure out where to go. And this is exactly how internet routing works, right? You send a packet, it goes to a router, the router checks its forwarding table, which is the distance vector equivalent, and that determines what link it sends the packet off to next. Okay. So distance vectors are like forwarding tables and routers, but just an abstract way of thinking about them. And the key thing about this distributed algorithm for computing distance vectors is that we share our distance vectors with neighbors. When we do that, we're telling the neighbor that if they want to reach a destination through us, if they want to use us as the next hop, they can use the distance vector that I'm sharing to figure out what the total cost is going to be by just adding the link that leads from them to me plus the values in my distance vector. That's going to be the cost to reach any of the destinations I know about. Of course, over time also, just as a added complication, you might not have a record of every single destination in the network in your distance vector. It might start off slowly and gradually build up as you learn about more destinations. We'll see how that works. Okay. So to calculate a distance vector, every node operates independently because it's a distributed algorithm. Like there's no time synchronization or anything. You just have a bunch of nodes that can run an algorithm. They can send messages to each other across their local links. They can only send messages to their neighbors. Okay. And what each node stores is some record of the outbound links that it has. Like in other words, what am I connected to locally? That's pretty obvious information. That's readily available. You need that information because you need to know how to use the neighbor's distance vectors. Okay. So in addition to those outbound links that are connected directly to you, what like the cost of those links, you also need to have a copy of the latest distance vector from each of your neighbors. At first you won't, of course, because at first no one has anything from their neighbors. But eventually, when you do get distance vectors you're going to get distance vectors from your neighbors, and you should keep the latest distance vector from your neighbor. And again, like I said before, you can use that combined with the cost, this item number 1, to figure out what the total cost would be to reach the various destinations using that neighbor as the next hop. So what each node is doing is running a loop of a calculation loop where each node can calculate its own distance vector using items 1 and 2, these two things it has. If it knows the outbound links and each neighbor's latest distance vector, it can compute an optimal distance vector by just choosing for every destination among all the destinations listed in all those distance vectors, which sum of outbound link cost plus the distance vector value, the cost from that neighbor, together provides the minimal cost to reach the destination. And whenever this information that I'm basing my distance vector on changes, whether it's the outbound links changing or the neighbor's distance vectors changing, like if a neighbor has an update to their distance vector, whenever that information changes, there's a possibility that my own distance vector should be changed to reflect that, right? So whenever any of this information changes, I need to update my distance vector. And when I do that, I also need to send my updated distance vector to my neighbors, but only do that if my distance vector changed. Otherwise, I'd be telling my neighbors that I had new information that wasn't really new, right? So if my distance vector changes as a result of things that I saw change, then I need to tell my neighbors about that because they might think that they could route through me with their information about the cost of routing through me is now out of date, right? I need to give them the latest information. And by following these rules, eventually we'll converge to an optimal solution. That is, everyone's distance vectors will be optimal. And you'll know that's true if no messages are being sent. The messages being the distance vectors that are being shared between neighbors. Okay. All right. So now I'll show an example of the distance vector algorithm in action in the context of one of the problems that sometimes arises later on. So we'll have a review of that in a couple more slides. But the network's not static, it changes. Links can be added or removed. The cost of links, let's say, can change. What happens when that, what should we do when that happens? So if this link, we have a simple network here of X, Y, and Z. The numbers on the edges are the costs of the edges. If a cost goes from 4 to 1 between X and Y, what should happen? Stop and think about that. Well, following the rules on the previous slide, we would know that X and Y would notice, they're connected to this link, so they would notice a change. So these nodes would recalculate their own distance vector because they have new information. And if their distance vector changed, they would notify their neighbors. Okay. Now, with link cost changes, we're going to look at two different cases. But we're going to call it good news and bad news. So this is a case of good news. So we have a link that became cheaper. That's good news. When this happens, it turns out that we converge to a solution very quickly. But for bad news, the problem is a problem arises where we continue to use old information. I'm asking you now to stop and think about when the link changes and you recalculate. If you're connected to that link, you have to recalculate your own distance vector. If your distance vector does not change, should you send your new distance vector to your neighbors? Should you send your distance vector to your neighbors? So hopefully you remember what I said before, that if your distance vector did not change, you shouldn't share it to your neighbors because your neighbors already have the previous version that you gave them, and therefore you just, it's a wasted communication and potentially a wasted recalculation that you'd be causing your neighbors if they weren't careful. Okay, there's no need to do that. And if you did that, actually, if the participants in this algorithm would always shared distance vectors whenever they recalculated their own distance vector, the algorithm would go on forever because you'd have, let's say, an update here at Y. Y updates itself. Y shares to X. X gets it, but nothing changes. But if nothing changes and it still advertises or sends its distance vector to Y, then that would repeat the process. Y recalculates, sends back to X, and so on and so forth. So what should happen is if either one of them notices that they got an update and that didn't actually materially affect their distance vector, in other words, it wasn't really an important update for them, they should just stop sharing information. Okay, so the alternative to that, to the flipped case, is when the cost of an edge becomes more expensive. We call that bad news. And bad news on the distance vector algorithm travels slowly. So when link costs are increased, the updates can actually be really slow because old information in the network is remembered by neighbors and may be used. So in this example, it might take 44 iterations for the algorithm to reconverge to the correct solution. Lots of back and forth, even though there's just one change. I'm not sure where that number 44 comes from. But I'll show you an example of this particular example in a second. We call this count to infinity because the neighbors think that after this change, the neighbors still have a record of the old distance vector from before that was using the old cost, and they try to use that old route, even though it's not. It was based on old information. So let me show you what I mean by that. What I was showing was this graph here, simple 3-node graph, and the change that's happening is that this 4 is going to change to a 60. Okay. But before that happens, let's just write down, make a record of what all the distance vectors are for all of these nodes. Okay, so before we have distance vectors for each one of these. So the distance vector for x is, I'm going to draw it as like a dictionary, right? So the destination is listed first. So to reach x, there's a certain cost that we know about. To reach y, there's a certain cost, and to reach z, there's a certain cost. Okay, because these are the three possible destinations in the network. Remember, but this distance vector stores for each destination the cost. Oh, sorry, this pen is terrible. Let me switch to a different color. The cost and the next hop. Oh, sorry, let's off the screen a bit. Okay, so previously, from x's perspective, it has a distance vector. Let's say that this algorithm ran for a while, and so it has converged to the optimal distance vectors. So for x to reach x, that's kind of trivial. The cost is 0, and you go through no next hop. I'm putting a null symbol there for no next hop because it's just itself. To reach y, looking at the numbers of these edges, we can see that we should go this way. So the cost is going to be 4. The next hop is y. To reach z, it's an indirect route, because if we went directly there, it would be 50. So instead, we go this way. So the cost there should be 5 through y. All right. So I'll go more quickly through the other ones. Because the other ones also have distance vectors. For y, we have the same destinations that can be reached, but the costs are different. So to reach x, the best option is to go through x, and the cost is 4. Or we can go directly to x in one hop. For y to reach y, the cost is 0. That's just the trivial case to itself. For y to reach z, the cost is 1, going directly to z. So y had like direct routes. The optimal routes were direct for all of those destinations. And for z, there's also a distance vector, of course, with the same destinations. And for z to reach x, the best way is actually to go through y, even though it does have a sort of direct route, but that direct route is costly, so the cost there is 5. And it goes through y. For z to go to y, we go there in 1 directly to y, and z to z is the trivial case here. Okay. So that was that's before. Excuse me. That's before the changes. Okay. The change that we're making is for this link of cost 4 to go up to cost 60. Okay. So we have it. So that was before. After that, at some point, the link changes. So we're going to say link changes. And now y is one of the two nodes connected to this link that changed. So y is going to notice the change. Let's say y reacts first. So y notices new information, and it recalculates its distance vector, which is just dv sub y. Now to do this, before I did it kind of quickly, but just to make this clear, to make it clear how these distance vectors are calculated, I'm going to show a little more detail. So y, when it's recalculating its distance vector, it has direct costs, which are the costs to use its edges, right? It has these edges available. So it can directly reach z in 1, and it can reach x in 60. Okay? So it has this information to go with. It also has distance vectors from its neighbors. So it has this dvx and this dvz. This dvy is not going to be used because what it's doing, it's recalculating its distance vector. So this is the one this one in the middle is the one we're recalculating using the new information. The information is my own costs and the neighbor's distance vectors, this dvx and dvz. Okay? So when we recalculate, we're going to get dvy prime, let's say, the new one. And this is going to be, to get this, we just, we go through all the possible destinations. How do we know what all the destinations are? Well, we kind of look at the information we have, which is this, this, and this, and we get a set of all destinations that are listed. So we have X, Y, and Z as all the destinations that are mentioned. And we consider them one at a time. So for X, we say, okay, what's the best way to reach X? I have two choices. For all these, I'm going to have two choices. I guess there's an implicit direct cost. I guess direct costs, maybe there's one more here that I should mention just to be just for completeness. I could say y equals 0. But that's not, we're not going to route with that because that's ourselves. So we'll just keep that in the back of our minds. That's a special case. Anyway, so for y to reach X, either it can use this link or this link. And if it's going to use this first link, the Z link, it's going to combine that with distance vector Z. If it's going to use the second link, it's going to combine that with the distance vector X. So to reach X, let's try Z first. The cost for using Z is 1 plus dvz sub X, which is 5. So 1 plus 5. On the plot, on the graph, what that means is this 1, the cost is this 1 plus the distance vector here. What the distance vector here says is the cost to reach X. Now, remember, Y doesn't have a complete picture. Y just has this picture here. So Y knows, I guess if we want to really draw it, this is what Y knows. Y knows its links, and it knows its neighbors and the cost to reach those neighbors. It doesn't actually know about this edge here. The knowledge it has about that edge is inferred. It's really just indirect through these distance vectors. So to reach X through Z, it sees a cost of 6 through Z. The other choice is to go through X, this other neighbor, which is 6. The cost is 60 for that first hop, plus 0, because dvx sub X is 0. So the choices are either 60 or 6. The minimum of that is 6, right? So the cost is 6, and the choice we made was to go through Z. Of course, that's wrong. The reason why we got this wrong is because it's based on this information here, which is out of date. So this distance vector we're storing from Z is still using old information about reaching X that was 5 that made use of the path through Y. You see that? 1 plus 4 is where this 5 came from. That 4 is no longer valid. Now it's 60. So really this should be 61. And the comparison we should have done was 1 plus 61 is 62 compared to 60 plus 0 is 60. And we should have actually went straight to the 60. But we don't have that information. We just have the out-of-date distance vector from our neighbors. So that's the main problem here, just that the other cases are simpler. So when we're recalculating the distance vector for Y, again, we consider these two possibilities, although we are Y, so from Y to Y is a special case of 0. Z is the other more interesting one. We either can go direct there in 1, or we can go through X in 60 plus what? 60 plus 5, right? Because we're going to X is the next hop, then from X, we're going to check the distance vector to see how what the cost is to reach there. So 65 or 1, obviously 1 is better. So that's what the distance vector will be for Y, okay? Y has updated its distance vector. So this one here is no longer, this one's gone. It's been replaced by this one. And it's going to share that with its neighbors. Now in particular, let's consider, let's say Y is going to share it to X and Z. Let's say that Z gets the update first. So Z gets the new dv sub Y, so Y's new distance vector. And then it must recalculate its dv, which is dv sub Z. Okay. Now to do that, just like before, if we're going to look at this in more detail, we have to say, okay, the information Z has now is its neighbor's distance vectors, which are this new Y1, this new y distance vector and the old x distance vector, because that's the one z has from before, and it also has direct costs for the edges that it can see, right? So it has a link to x in cost 50 and y in cost 1. So when it recalculates dvz prime, the destinations are x, y, and z. But let's just start with this, get this easy one out of the way. From z to z, we know it's going to be 0, because that's itself. But for the other two, let's consider x. So to get from z to x, z has to consider what two options? These two options, right? Either going through x or y. So the option that goes through x is the cost is 50 plus dvx 0. So the first option, the cost is 50. The second option is 1 plus dvy sub x, 6, right? So again, we're considering going to y. Sorry, we're considering going to x through y. The cost is the first hop going to y, and then y to x. Y to x is 6. So that's 7, which is going to actually be smaller than the 51 that we got before. So 7 through y. Now, of course, that's wrong. Okay, so again, this is wrong. Put an asterisk here. Because, if you look at this graph, there's no way to go from z to x in cost 7. What we're doing is we're kind of reusing this old information in an indirect way through y. So we're going up here. That y information that we're using is through z. So actually, we're kind of going like this. We're going up 1, 2, 3, plus 4 is 7. That's where the 7 comes from. Bloop, 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 bloop. Which is just totally wrong, right? But it's because we're using old information that was propagated through from my old distance vector carried through to a neighbor's distance vector, which I just got, and then I use it. For y, it's still going to be 1, so that's not too interesting. So what you see here is that in 2 rounds, the distance vector for z and y are still out of date. So we're kind of slowly getting closer. But if this can actually propagate back and forth with these numbers for the costs of reaching x going just up by 1 each time. Okay, what we really want, in reality, the distance vector for y, let's say, to reach x, the optimal is what? 51, right? We want to eventually choose this choice. Instead, we're trying indirectly by using this route, this edge here, plus the old 4. We're getting this other bogus number. And but every time we're increasing by 1. Where's that 1 coming from? You stop and think about that. Why is it increasing by exactly 1 each time? It's because this cost here is 1. We're adding another use of this edge here bogusly, because it also is combining the old value of the 4. Okay. But eventually when we do this, these numbers will keep going up until they're greater than 51, and we'll choose the actual better choice, which is 51. Okay. All right, so that's how distance vector can go wrong if we implement it in like the simplest possible way. Now, we don't want to use an algorithm that does that. Notice in particular that if that edge, instead of going up to 60, if it went up to like infinity, like for example, if this edge just disappeared, the way we might represent that in our graph is that the cost is infinity. In that case, we really would count to infinity, and that would take infinite time, right? So that's no good. What can we do to avoid this? Well, you can stop and think about it, but it's kind of a tricky problem. If you read the book, you might know the answer just immediately. But what's the fundamental problem that we had? We were reusing a path that went through me. So like if we look at this case with x and y, when y made its bad choice here, it was choosing to go through z, but then z was in this old route of that z was going through y. So y was trying to reach x, by going through Z, and Z was going through Y. So it was a back and forth. It was a loop. Okay, so that looping is obviously never going to be efficient and never necessary. So if we can eliminate those loops, that would eliminate the count to infinity. So we can implement what's called a Poisson reverse, which is a rule where we just say if Z routes through Y to get to X, then Y should never choose Z's route to get to X, like what I just said, basically. So if you list what the next hop is and you include that in your distance vector, so if here when Y was considering who to use for X, when it said, okay, let's consider Z, if it looked not just at this number 5 and the 1 plus 5 equals 6, the 1 plus 5 equals 6 looks great. However, this other piece of information, this Y, should have been a warning to Y. If Y had this information and it looked at it when it was considering that option and say, oh, Y, that's me. Why would I ever route through me? Why would I ever route through someone who's going to pass the packet back to me to reach some other destination? That makes no sense. A Poisson reverse is a rule that eliminates those kind of options. But actually, that's not a total solution because the next hop doesn't prevent you from loops that involve more than 3 or more nodes. That was what we showed here was a loop of 2 nodes. So if knowing information about the next hop is enough to prevent you from doing loops with 2 nodes, can you think of ways to expand that, generalize that to avoid loops with more than 2? It's a little bit tricky. Basically, what we can do is list the entire path instead of just the next hop. Instead of just the next hop, if you know every hop that's going to be taken. So if we look at this picture here, if this was not just the next hop but a list of every node that was going to be used, then we could check that list for myself appearing in it and use that to invalidate the route from consideration. And that's what's done with BGP and the AS path, which we'll come to later on in the lecture. Okay. So we've talked about different routing algorithms, centralized algorithms and distributed algorithms. So the centralized ones are easier to reason about, so you can kind of prove upper bounds for message complexity and convergence speed. It's less easy to reason about a distributed algorithm because it really depends on, the behavior depends on what order things happen in. I guess you could assume the worst case order, but I think even then, I think you can design a simple, a good algorithm like the distance vector algorithm, but then choosing an adversarial ordering of actions might, I think even for a good algorithm, lead to things never converging. We had a count to infinity problem with the distributed distance vector algorithm. There's something similar that can happen with the link state algorithm if you are propagating those updates to everyone, which is called an oscillation. But we're not going to really look at that, although you might see that when you implement Project 3. If you think about routers malfunctioning, so like those individual nodes behaving badly, whether maliciously or because of a coding error. In the case of a centralized algorithm, what we're doing is having the routers share their link information to the whole network so that every node will have information about the whole network and can solve the shortest path problem with complete information. So a single router going bad would mean that the link cost was advertised could be incorrect. For just a distance vector algorithm, there's actually more bad information that can be shared because you can advertise a path that involves like a whole chunk of a network and attract traffic that you shouldn't get by claiming that you're close to everyone. Which will make more sense when we look at the BGP. But I guess if you just a way to visualize this, if let's say this node X, it's advertising its distance vector to its neighbors. If it changes these numbers, and if it says, like, for example, I can reach not just X, Y, and Z, but I can reach, node G in cost 1, but it's actually not connected to G. That might cause its neighbors to send traffic to it that is destined for G, and then X might just drop that traffic because it doesn't really have a way to reach G. So malicious activity or buggy behavior here can cause traffic to cause what's called a BGP black hole, which is kind of bad. All right, so this is switching slightly to a new topic here. So feel free to take a quick break before this. Well, let's talk about how those abstract algorithms get implemented in real life with BGP and its friends. So the internet actually is not treated as one big network graph and a shortest path problem solved over that. Okay, so there are too many routers. There are about over 100 million routers across the whole internet. That would make a really big network graph to solve a shortest path problem on. And sharing that information to everyone, all that would create n-squared messages being communicated, which is a lot of information. And any one change would have to be propagated to the whole network. So using a centralized algorithm wouldn't make sense. And also, even trying to do a distributed algorithm that was operating on a huge network would be difficult because there'd be a lot of updates all the time. So what actually happens on the internet, this is kind of surprising, is that routers are broken up into groups called autonomous systems. And I'm showing that with the blue blobs here. So instead of having a network with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 routers, we have a network with 3 autonomous systems. And we solve a routing problem over those 3 autonomous systems, which is kind of creates a higher level zoomed out view of the network. And then we also have routing problems that are solved internally, but those are only relevant for communication inside. For communication that happens on the large scale across the whole internet, the main thing you need to know is, first you need to figure out how to get out. So you need to use figure out the shortest path to get to the edge. Then from there you use this high-level autonomous system routing solution to find that shortest path. And then when you get to the destination, again, you have to figure out the shortest path within that autonomous system. So it's like a 2-level thing. At the low level, you have to figure out the shortest path. You get to the high level, figure out that shortest path, and then again you go down to the low level to figure out the shortest path. For example, going from 3C to 2B, there would be 3 stages. So by doing this, so not only do we make the problem smaller, we also create administrative autonomy, so the internet can kind of behave like a network of networks, where if these autonomous systems are different, they're different companies usually, or organizations. Like one of these might be Northwestern's campus. Within each autonomous system, a different routing algorithm can be used, and that can be managed independently. Okay, so the autonomous systems, like I said before, are groups of routers that cover campuses or data centers, but just nearby routers that are operated by one entity. The internet has about 100,000 autonomous systems, and that defines the number of nodes in the internet graph that we're solving the shortest path problem on. So 100,000 is a lot better than 100 million, especially since the cost of solving the problem doesn't scale linearly. It's much more. It's like n log n in the best case. So all these autonomous systems have numbers. We call them AS numbers, autonomous system numbers. These are distributed by the ICANN. Remember our friend, that organization, that global organization that distributes IP addresses and manages domain names. They also manage autonomous systems. And by getting an autonomous system number, you are able to participate in the Border Gateway Protocol, BGP, connect to other autonomous systems and have traffic routed to you and route traffic to neighbors. Okay, so autonomous systems have a bunch of routers that are connected to each other, and they have gateway routers, or also called border gateways. That's why BGP is the letters Border Gateway Protocol. It's like the protocol followed by these border gateways, which are the routers at the edge of the autonomous systems that connect to other organizations. Okay. There also are interior gateway protocols, or IGPs. They're different ones. that are used to figure out routing inside an autonomous system. But between autonomous systems, there's only one standard protocol, which is BGP, because everyone has to cooperate to solve that problem together to make the whole internet routes, the global routes, correct. Okay. You actually can browse a list of autonomous systems. That's kind of a fun exercise, so I encourage you to do that. The ones at the beginning are the companies and universities that were like present at the very beginning of the network. Like Level 3 Communications is one of the biggest Tier 1 ISPs. You see universities that were involved in the very beginning of the internet. But if you go further down, you see other, just like more companies, and there are about, like I said, tens of thousands of these. For example, Northwestern is autonomous system number 103. So Northwestern got on the internet pretty early. But, if you look at autonomous system number 32,401, we have HMart, the Grand Super Center Incorporated. So this is like the grocery store out in Morton Grove that sells Asian groceries. They have their own autonomous system, I guess because they manage a network. I assume it's the same HMart. Not 100% sure. All right, so BGP is used for routing between autonomous systems. We're going to spend the second half of this lecture talking about that. But before we do that, let's talk briefly about interior gateway protocols, or IGPs. This is for Intra-AS, but is within an AS routing. So a network operator has full control. So if you have different autonomous systems, they could be using different interior gateway protocols. So in this example, I'm just listing 3 different examples of protocols for finding the shortest path between routers. And different ones could be used by different neighbors. Because they only operate within the autonomous system, there's no need for coordination and standardization. Like it's okay that a different algorithm is used here compared to here. And there are different ones of them that you could look at and remember their names. So basically, they're both centralized IGPs and distributed IGPs. So link state algorithms that implement Dijkstra's algorithm are commonly used inside. I think those are more common, but there also are variations that use a distributed distance vector style algorithm internally, like RIP. One popular interior gateway protocol is the open shortest path first algorithm or protocol. It's called open not because it's the paths are open, but because it's open source, and it actually can operate in a hierarchical manner. So this works well for a really big autonomous system, and where you can figure out the shortest paths, for example, within these branches, and then find the shortest path at the higher level and solve that. So overall, the routing on the internet is not just happening at 2 levels, but could be happening at 3 levels or 4 levels if you have one of these multi-tiered interior gateway protocols. But and notice that what we have here, this example is showing an autonomous system that has a lot of routers and has one boundary router, or border router, what we should say, that connects to the rest of the internet. So this top router would be using both the interior gateway protocol to coordinate among these internal routers about what the shortest paths are to reach all these destinations, but also using BGP, the border gateway protocol, to coordinate with the rest of the internet about the best ways to reach itself and the best ways for it to reach the rest of the internet. Like I've said before, BGP, the border gateway protocol, is used for Inter-AS, so within autonomous system routing, the global internet routing. And this is the glue that holds the internet together, right? So BGP is really important. It's fundamental. Just like TCP is another fundamental protocol, BGP is at that same level of importance. It technically has 2 parts. There's eBGP. Mostly what when we say BGP, we're mostly talking about the external BGP protocol, which is how neighboring autonomous systems share information about what subnets can be reached. There's also an internal BGP protocol that's used just to share information within that was gained by the external protocol internally. But the really interesting thing is the external border gateway protocol, eBGP. So you have all these autonomous systems that are advertising to their neighbors about what IP addresses they have, and what IP addresses they can reach through their neighbors, which is equivalent to the idea of the distance vector approach, where you advertise what neighbors you can reach. So the distance vector, we can compare distance vectors in BGP. So the reason we introduced the distance vector algorithm was as a way of introducing BGP. Kind of like if you remember with the TCP chapter, first we introduced reliable transport in general, and then we moved to TCP. TCP is the real thing. That's the same thing here. Distance vector is the abstract general way of doing a distributed shortest path algorithm, and that translates into, we can translate that into BGP, which is the real implementation of something like that abstract algorithm that has more complexity and details because it's dealing with IP addresses and autonomous systems, but the basic idea is the same. Okay, so I'm showing these distance vectors in this case as a 2D array instead of a dictionary, but the first column basically is the key, is that destination. For every destination, we have a cost for the path and a next hop. All right, this is the same as what I was showing you before. Destination, path cost, next hop. The only difference here compared to my example is that I'm using numbers for the nodes instead of letters, but that's not an important difference. When we look at BGP, we translate that, and instead of having destinations that are like router numbers or router letters, we have subnets. So these are chunks of IP addresses that are destinations. Okay, because we want to use this to be able to reach different IP addresses. Instead of the cost being one number, we have the path, the AS path, which is to say the autonomous system path, the numbers of autonomous systems that we will travel through to reach the final destination. Okay, so what this means is we're going through 3 hops. The first hop is autonomous system 2, the second hop is autonomous system 34, and finally we go to autonomous system 3. Okay, that is not that is the kind of cost that we use in BGP. And actually, the way we use that as a cost is just by using the length of the AS path. So the cost of this one is 3. The cost of the second one is 2. We don't have edge costs actually in BGP. That's pretty interesting and kind of disturbing at first to students learning this. We don't have edge costs. We consider every edge to have cost 1. The only thing we care about is the number of edges, the number of autonomous systems that we travel through. And we list them all out instead of just having a number because, like I said before, we want to avoid loops in routing. Instead of having a router number for the next hop or a node number for the next hop, we have an IP address for that router, but it's the same idea. We can use that to send the message to the destination. So with this BGP advertisement, we also have a different name. Instead of calling it a distance vector, we call it a BGP advertisement because this is what we're sending to our neighbors. Just like distance vectors were sent to neighbors, BGP participants will send information to their neighbors. They will advertise to their neighbors, what hosts can I reach? What's the cost to go there through me? And what autonomous systems will the packet travel through? And if you want to send it there, what IP address should you send it to? Okay. So I kind of covered this, but just one detail is when we have these neighboring border gateways, they'll have a session which is an open TCP connection that's semi-permanent that's used to send messages back and forth. So it's kind of a peer-to-peer protocol. And the messages that are flowing back and forth are these BGP advertisements, which are like the distance vectors. When an autonomous system advertises a prefix, a destination, to a neighbor, it's telling that neighbor what the cost is to reach that destination, but it also at the same time is promising that it will forward packets to that prefix if those packets are given to it. So if in this picture, AS3 is sending a BGP message, an advertisement to 1C, if that has a certain destination listed in that advertisement, that is telling C not only what the cost is to reach that destination, but in fact that AS3 is willing to accept packets that are going to that destination, and it will forward them to that destination. Okay, it doesn't have to do that. It's actually that's something in the control of the autonomous systems. They don't have to advertise everything. They can keep secrets basically. If they want to keep a secret, that will prevent a neighbor from sending traffic that goes to that destination. But if you keep too many secrets, your neighbors won't like you in life and in BGP. Okay, so BGP advertisements, like I said before, are distance vectors in practice. Here, this pink line shows more neatly what might be on a single line of a BGP advertisement. We have a prefix, that's the destination. We have a path, which is a set of autonomous system numbers. The length of that path is important. That's kind of the cost of the route. And we have the next hop, which is the IP address of the router that begins this path. So if you want to use this this route, you send a packet to this next hop IP address. Okay, by doing this, by advertising this route, an AS would be advertising that the neighbor can send traffic to this particular subnet. Like any IP address in this range would be accepted. It'll take 3 hops to get there. It'll go through these particular ASs, and to make use of it, send your data to this IP address, this router. That's the next hop. Okay. We saw that BGP advertisements include the full AS path, which is a list of autonomous systems that will be traveled through to reach the final destination that's advertised, that subnet. Why is that full path advertised instead of just the length of the path or the cost of the path? This is a review of something I already said, so stop and think about that. Do you remember that? Well, the reason for this is for routers to prevent loops. This is specified in RFC 4271. AS loop detection is done by scanning the full AS path and checking that the autonomous system number of the local system does not appear in the AS path. So for example, if I am AS0 and I receive a route advertisement with path 2405, I should not use it. It doesn't make any sense for me to use that, because this is saying that this path will send the packet out for a couple hops, it'll come back to me, and then I'll have to deliver it to someone else to complete the delivery. If that's the case, then I should just follow this last step, right? Why would I send it out to come back to me so I can complete the delivery? That's by definition a loop. Loops are bad. Okay, so that's how BGP finds the shortest path on the internet. There's more to BGP and internet route selection than just finding the shortest path, though. That shortest path part is step 2 here in a sequence. Okay. First, we actually can have local preferences. So an AS can basically hard code preferences. So what this means is this would be a rule, which is a destination, like a subnet destination, combined with a next hop. And you might just hard code that and say, like, for example, whenever I send data to, if you're Northwestern, you could say, whenever I send data to University of Chicago, I'm going to specifically choose to send it on the Internet 2 router, as opposed to just sending it to whatever is the shortest path, because I know that I have an idea that particular route I'm choosing is a good one. Maybe it's cheaper, right? Maybe I know that the latency is lower, because there's nothing in BGP that takes into account latency. Maybe I know that the bandwidth limit, maybe I know that's a really high capacity link. Again, the capacity is not taken into account with BGP either. So there are many reasons why you might want some kind of local preference. The BGP rules I defined for finding the shortest path is about keeping everything connected and making sure there is a valid path and that it's the best in some very limited sense. But in reality, the true details of the network globally are never truly shared and optimized across. There's a lot of like manual tweaking that happens based on cost, capacity, latency. And the way that's implemented, we could think of that as a step 1 that happens before that BGP stuff, where there's a local preference of hard-coded rules for what path to take, what next hop to use for certain destinations. After that, we use the shortest AS path that was determined by this distance vector-like algorithm that BGP is doing. But even that is not enough, because there could be ties. Remember, we're just using the number of AS paths. This is going to be a small number, so it's very easy for that to be a tie. If there is a tie, we use hot potato routing, which is to say we try to get rid of the packet as quickly as possible, right? Hot potato is difficult to hold, right? So you want to get rid of it as quickly as possible. And what that means in the context of internet routing is that we try to push it out of our AS as quickly as possible. So if we have two options to reach a destination, same number of hops, those are hops outside of our network. So we just send it out. We just try to get it out of our network as quickly as possible. So we use the shortest number of internal hops or the shortest internal latency, depending on what internal. So the interior gateway protocol is going to determine how that tie is resolved, that hot potato routing. Okay. If there still are multiple options, then after that, like if the IGP doesn't break the tie, or if you only have one outbound link, but you still have multiple, if the interior gateway protocol is not able to break a tie, then you can use a random tiebreaker like the BGP router ID. But the most important things are these first three things, and that BGP shortest path optimization is really just in the middle. It's not the entire story for route selection in practice. But when we talk about BGP, I guess really we're talking about the step 2. So BGP tells us what autonomous systems we want to travel through. But in order to figure out the forwarding table at a particular router, you have to know a little bit more than just that. You have to know, where, like if you're at position 1D, shown here, I mean, BGP might tell you, great, you need to go through AS2 to reach a destination, but you also need to know how to get to AS2. So those first few hops within your own system are going to be determined by your Intra-AS routing algorithm, your interior gateway protocol. So that will be computed internally and shared, and so these internal routers will know how to reach themselves, all these internal destinations, in the shortest possible manner. So when reaching an external destination, like let's say it's this IP address 2A, the interior gateway protocol will tell you what the right next hop is to get you to 2A. Do I go left or do I go right? I mean, probably what we want to do is go right in this case, and the interior gateway protocol would tell us that. So we combine that with the results of BGP. BGP would tell us first we need to go to AS2, and the interior gateway protocol would tell us how to get to AS2. In other words, specifically the next hop is 1B. And then 1B would have its own, would use its information to know that it needs to forward this way. Okay, so to review a little bit of why we have different intra and inter-AS routing algorithms, in other words, why do we have interior and gateway protocols as well as BGP? There are different needs at the different levels. In terms of policy, when you're talking about between different organizations, you have more need to control policy. So you want to have an ability to hard code rules, and BGP gives you that. BGP also lets you advertise different rules to different neighbors. In other words, BGP lets you keep secrets. Whereas if we're just routing internally, you probably have within a single administrative zone, you don't really care. You probably don't care about hard coding rules. You just want to optimize for the shortest path. Although maybe that's a little bit of a simplification. You might still want to optimize for certain technical characteristics like bandwidth and latency. But what's for sure is that having two different sets of protocols helps with scale. So when we have BGP just operate on about 100,000 nodes, it's much easier to do. And the amount of update traffic we have at the high level is reduced, because any changes that happen internal to an autonomous system only affects the interior gateway protocols. The whole internet doesn't have to know about it. The whole internet just cares about that high level. What AS am I going through? Not internally, like what paths are being taken by the routers, by the packets inside that AS. Like notice in this previous example, like let's say I'm going from 3 to 2. The way 3 thinks of it is like from 3C to 2B. AS3 has to know how to get to 3A, and then 3A has to know that I go to AS1 than AS2. I mean, in practice, though, there's a lot. When it gets to AS2, there's more information there's more detail that's needed. So if that packet arrives here on 1C, it can't just send it to AS2. It has to send it down here. So it has to know the internal path. Those internal paths are determined by the different internal gateway protocols along the AS path. Okay, there's more to come. So what we're going to do next is go through an extended example of how BGP works to try to reinforce these ideas. Okay, so this example is going to use 6 autonomous systems. So we're going to imagine we're just working on one /12 subnet. So the 1.0.0.0/12, you can see different parts of that are distributed here, distributed to these different 6 ASs. It's not super important, but the sizes of the chunks are different. So we have the top 4 have a smaller number of IP addresses than the bottom ones. And each autonomous system has a number between 0 and 5. Well, this one is 6. Maybe this one should have been 5. Anyway, there are 5 different autonomous system numbers. And they all have neighbors that they can communicate with. Okay, so each of these pink squares is an abstraction that hides a lot of details of an internal network. So this first one in the upper left might be Northwestern. This next one to the right of it might be Comcast. The one below it might be University of Chicago, and so on. And they all have connections to different organizations. Those are shown as the black lines. They also have internal stuff that we're not seeing at the external BGP level. One little detail here, I also introduced additional IP addresses in the 2.0. whatever range for the border gateways to use for convenience. So because they have to be on this, the thing is, if you think carefully about what we learned before, for 2 routers, these border routers to talk to each other, they need to be on the same subnet. So you need to be sharing IP addresses within a chunk. Now in practice, how that would work probably is that if this first autonomous system wants to talk to the one below, it might use one of its own IP addresses and then give one of its IP addresses to a neighbor so that it could communicate with it. And then each of these routers has different IP addresses for the different internal connections. But again, for simplicity, I've just introduced a new subnet, a new range of addresses to use for the border routers. Okay, so the first iteration through this is going to assume basic shortest path routing, no local preference. So we're going to see how BGP implements a distance vector algorithm for computing the shortest path and converging to a solution that optimizes for the minimal AS hop count. In other words, to reach a destination, we're going to travel through the minimum number of organizations. Okay. BGP routes, like I said before, have 3 things: a destination, the cost, and the next hop. The destination is expressed as a range of IP addresses, a subnet, basically, a prefix. Not subnet's the wrong word, a prefix. But it looks like a subnet. The cost is expressed in terms of a list of ASs, and then the next hop is an IP address. Okay, so if we look at this upper left autonomous system number 0, we would expect eventually its routing table to look like this. Okay, so it's the list of different destinations it can reach. These are just all the different blocks of IP addresses in this universe, 6 different destinations, 1, 2, 3, 4, 5, 6. And then we can look at the picture to see what the shortest path should be and write it down. So to reach itself, there are no hops, and the details of which, of course, there are going to be details to reach the different subsections of this range, but we can't see at this view what the internal routers are and how they're connected. So I'm leaving off those details here. But this is just kind of going to itself. The next one I have listed here, 1.1, is the AS to the right. And to reach that, we are going to send traffic to 2.0.0.2, which is this router on the right-hand side. So notice that for all these destinations, actually, the next hop is always going to be either 2.0.0.2 to the right, or below 2.0.1.2. So either we're going to go to AS1 or we're going to go to AS2. Those are our only choices for the next hop, regardless of who we're reaching across this whole little intranet. And of course, depending on where we're going, the number of hops in the particular ASs we travel through are different. If we look at AS3, we actually can reach it in 2 different ways with the same hop count. 2 hops, whether we go to the right or to the bottom. So I'm listing 2 possibilities, actually, and we're going to make use of both of those, actually, depending on what we use internally. Remember that those kind of ties are broken with hot potato routing. Okay, so if we zoom in, we actually can see some details of Autonomous System 0. AS0 has many routers, not just one. I mean, not just the two that I showed at the borders. It has 2 border routers, which I showed before. It also has some internal routers. I'm showing a topology of the network, how they're connected, and I'm listing latencies between the routers. And I'm assuming that the interior gateway protocol is using the latencies to solve for the routing. It doesn't have to do that. I'm not sure how common it is for that to be used. But again, internally, we have the freedom to use whatever protocol we want to choose the shortest paths. We're not stuck using BGP. It doesn't have to be standardized across the internet. So, personally, I feel like it's logical to use shortest latency paths. Okay, so let's draw those. So if I'm trying to reach the destination 3, whether I go to the right or down for the next hop, it doesn't matter in terms of the AS count, but in practice, we would want to go in the direction that lets us get this hot potato out of our hands as quickly as possible. In other words, we want to get rid of the packet as quickly as possible, so we use the shortest internal path. So if we're in this position up in the upper left, we can get out in 1-2 milliseconds by going to the right, whereas going down we go 2 + 1, 3 milliseconds. So the bold lines here show the shortest path trees for reaching the border gateways. And so the top 4 routers would go right, and the bottom 2 would go down to reach the tied destinations, whether it's 3 or 6 that we're reaching, both of those cases. Okay, so that's how the tiebreaker works. All right, so traffic flowing to these 2 ASs would go along 2 different paths depending on where it's coming from. Okay. Internally, we use the interior gateway protocol to build the forwarding tables that exist at the different routers. Now these routers they're all part of one autonomous system, but they're going to have different detailed forwarding tables because they have to travel through this internal network before they go outside. So if we're looking at this router in the lower left, 1.0.0.1, it's going to have the same destinations I listed before for like the internet as a whole, but the next hops that are available to this router are not 2.0.1.2 and 2.0.0.2. It's not connected to these border gateways. At an AS level, yes, these border gateways of my neighbors are the 2 possible next hops, but at a more detailed level internally, the next hops available to these internal routers are the ones that are located nearby. So these 3 are the 3 next hops available to this router in the lower left. So all the next hops I have for these different destinations will be chosen based on which direction I need to go in to reach that border gateway. Okay. And that'll be different for each of these internal routers. One of the details that's kind of glossed over here, I'm showing one IP address for all these routers. In practice, the routers have one IP address for every link, for every subnet that they're on. But I'm not going to show that because it's just going to make the drawing a lot more complicated. Okay, so this router down here has a choice of either, basically, you'll see in the final forwarding table, it either is it goes up only for this sub part of AS0. Notice that these rules now break AS0 into multiple pieces. So 1.0.64.0/18, the IP address is up here. It's going to go up for these other internal ones, it's going to go maybe to the upper right to this other router, and also to reach some of the external destinations like 1.1.0.0/16. This prefix here is an external internet. It's outside of the AS. It's some other organization, but I'm going up right to this router to reach there. But for some of these other external destinations, I'm going to this other internal router. There's some redundancy here in these rules. So what we want to do is actually aggregate them. Okay, this is a copy of the same rules. Okay, the one that's listed local, those are the IP addresses responsible under that particular router, where it can just send them directly without. It's on the subnet itself. But a lot of these are redundant. Okay, so in particular, there are two aggregations that can be made. These two go to this one, and these four go to this one. Okay, and this bottom one actually, if you look closely, you'll see it contains some of these other ones, but that's okay because longest prefix matching is used. To see why that's the case, how these aggregations can happen, you need to look at the bit level detail. So this is kind of a review of some of the things we covered in the subnet part of the class. But so those first two, if you write them out in binary, you have, I'm putting X's where the subnet allows for arbitrary bits. So these are /18, so we have 18 zeros or ones, and then after that we just have don't cares, X's. Now notice that when we put these next to each other, the first 17 bits are all the same, and the 18th bit we have both options that are covered. And remember, both of these were going to the same destination IP address. So we're saying that these two prefixes should be routed to the same router, and those can be expressed more concisely by just having one rule, a /17. Okay, because this we have both options present for the this bit in position whatever this is after 17, the 18th position, going from high to low. The second aggregation that I showed was more complicated. It involved lots of different prefixes. And I guess these four prefixes all map to one IP address. There's one router being used for these four. And if you can write out a lot of IP addresses and do the same thing. So I don't know if this doesn't actually particularly match the previous slide because different routers were used, I think, for those. Yeah. But anyway, these prefixes, these 1, 2, 3, 4, 5, 6, 7, 8 prefixes, all can be combined into 1.0.0.0/12, because if you look at the bit representation, the bit level representation of all of these, we can kind of round them up and combine them. So the 0 and 1 here can become a don't care because all the prefix bits are the same. So we end up with, so that covers so we have 0, we have .0x. We also have the .1x here, so that covers that. So these low bits are not needed. At the higher level, we have the 0 and the 1 both, so that eliminates that position. Then at the 1 position, we have both options there. So then we have the 1 and the 0 both. That covers that. And then we have the 0 there and the 1 here, and so on. So it's a little bit messy, but these are all equivalent to. These are just a really long way of saying this one pattern broken up into different levels, I guess, here. And this one pattern is a /12 prefix, because there are 8 plus 4 bits in a high position that are fixed. Right. Okay. So I want to take you through BGP working step by step from scratch without any previous information about neighbors. So this is kind of like going through distance vector bootstrapping, but with all the details of BGP, or most of the details of BGP. So we're gonna focus on this autonomous system 0 in the upper left. Okay. So at first, all it knows about is itself. So it knows this block of IP addresses 1.0.0.0/16 can be reached directly. So that's I have an empty AS path, and local is listed as the next hop because the details will be determined by the interior gateway protocol. But this is information it can share with its neighbors. So it knows about itself. It happens to know that it has connections to two neighbors. Those are physical things it can observe. And so it advertises. It shares its distance vector, in other words, which is to say it does a BGP advertisement. It takes this information it knows and it shares it to these two neighbors. Now, some of the details are different for the information it shares left versus the information it shares down, because the next hop IP address is a little different, right? These two neighbors are not connected to the same router on AS0. Whoops. They're not connected to the same router on AS0. They're connected to different positions on this autonomous system. So when AS0 tells AS1 that it can reach this subnet, the next hop it needs to advertise is the one that is connected to AS1 compared to the different one that's connected to AS2. Okay. And of course, the neighbors will do the same thing. They'll be aware of their own IP address ranges and they'll advertise that to their neighbors. Okay, so you can see that here. And notice that when an advertisement arrives, the interior BGP protocol, interior BGP, which we haven't really discussed, but the main purpose of it is to share information received at the borders internally. So for example, when AS2 does an advertisement to AS0, it'll be seen by this one router that gets it, but iBGP will share that information also with all the other routers, including this one here. So that all of them can make use of that information. So after hearing from neighbors, AS0 now has an expanded view of the internet, right? It now knows not just about its own range it can reach, but it knows about these other two ranges that it can reach through two neighbors. Okay, so it can see about half the internet now after one cycle of sharing. Okay. Now, the cycle will go on because AS2 will learn about 4 and 3 and so on, right? So as more information is shared, AS0 will learn more. So if we want to look at one way of getting there, let's look at the neighbor to the right, AS1. If we assume AS1 has already heard all of the information from the rest of the internet, and AS0 is the only one that's kind of slow or behind, then the routes AS1 is going to have are as shown here. Okay, you can kind of stare at them to see whether they make sense. So basically, these specify the different destinations, all these 6 different destinations, and what the proper next hop is from AS1's perspective. So either it's going to go down or to the left, right? It's going to go down for all these ones down here, except it's going to go to the left for AS0. I guess some of these are ties. Like it could go to the left for AS2 and AS4, but in this particular case, I'm showing them as going down. I'm assuming that I'm assuming that actually no. This is how it would be fine because AS0 has not yet learned about AS2 and AS4. That's what it's assuming. It's assuming AS1 has heard information from these 4, but it has not heard very good information from AS0 yet. Okay. So AS1 will send an advertisement to AS1. One will send an advertisement to 0, as shown with this arrow. So to do that, AS1 takes its own routes and it modifies them in a way that makes sense as an advertisement to its neighbor. So in particular, it adds AS number 1 to the beginning of all the AS paths. So what was previously stored internally was just the information that's needed, which doesn't include itself at the beginning. But then also, AS1 needs to know the next hop to reach different destinations. Like for example, getting to 6, the next hop is this 2.0.3.1 down here. But that should not be advertised to the 0 because instead AS1 needs to advertise that it is becoming, it's advertising that it will act as the next hop to reach all the destinations it can reach. So basically it puts its own IP address of the router that is on the border with the neighbor when it does the advertisement for all the destinations. Okay. And that'll be received by AS0. When AS0 gets that, remember, we're assuming that AS0 is just bootstrapping with very little information just about these two neighbors. Formerly, it only had 3 entries. It only knew about half of the internet. It gets an advertisement from AS1 that has this information, like a lot more information. Some of it is redundant, and but some of it is new. Some of the new information is inferior. So for the second piece of information in the advertisement says, AS1 is saying I can reach you in 2 hops. Well, AS0 doesn't care that it can reach itself, and it can see the 0 in there to know that that's a loop, right? So that is clearly worse than the record it already has for reaching itself. Another example would be reaching AS2 down here, the 1.2.0.0 destination. 1 does advertise to 0 that it can reach that it would be able to forward packets to get there in a total of 3 hops if AS0 wanted to do that. But AS0 is not going to choose that because it already has a record up here in the 3rd bullet point where it gets there to that same destination in only 1 hop by going directly down instead of right. Okay, but among this advertisement, there is new information that's useful. Not that inferior, apart from that inferior information I mentioned, there is information about reaching AS3, AS4, and AS6. That information is not at all available. There's no prior, better way to get there that's known to AS0. So that will all be added to AS0's routes. Okay, this is like a distance vector update. Previously, it saw it had like the cost to get there was infinity. It found a better way, so it adds that to its routes. Okay. So after it gets that information, it might also get an update from AS2. So on the top here, I'm showing what we just arrived at, the information, the distance vector that we have, or sorry, the routing table that we have, the routes we have after AS1 advertises. AS2 now advertises to 0 with some information. This includes an inferior route, which is not used. In other words, to get to AS1, similar mirror situation as before. AS0 doesn't care that it can get to AS1 in a total of 3 hops through by going down because it already has a way to get there directly in 1 hop. There is one thing it advertises that is better though, and I've highlighted that in purple. So you can see that previously AS0 learned about AS4 from AS1, and it could get there in this red route that goes in 4 hops. But AS2 has just advertised that they can get there in 2 hops. So the 2 plus 1, or sorry, the 2 hops is better than that 4. And AS0 will do an update for that shorter route. It might also store some equal alternatives. For example, getting to AS3 now has ways to get to AS3 and 6 that are new and equal in length to the ways that went through to the right. So it can go down in 2 hops to 3, or it can go right in 2 hops. It'll save those because some of the routers in here might be able to get there faster with hot potato routing. So half of these routers, roughly, will go one way, the other half will go the other way. It's worth keeping that information because it provides a shorter path for some of the routers. Okay. All right. Those are the basics. Now let's think about some subtleties. So AS0 now has 2 routes stored. One of them has a route to get to directly to 2. Okay, sorry. What this is showing is it's rewinding us a little bit to the situation right after AS0 got an advertisement from AS1, but before it got the advertisement from AS2. Okay, so in this previous slide, I showed an update from this to that. But you may wonder why couldn't we just get there originally through inference? So why did AS2 need to tell us it could get there? In other words, previously I knew once AS1 told me that there was a path of 1, 3, 2, 4 That's when AS0 discovered 4. AS1 also knew at that time that it could get directly to 2 in one hop. So maybe it should have looked at this and said, "Oh wait, I can rewrite this. I can shortcut this, like short circuit it, and go directly to 2.4. I can infer that there's connectivity directly to 4." Now, I want you to stop and think about that. This is a little bit tricky. So it's true that AS0 could make the inference that there is that there might be a path that way, but it doesn't do that for 2 reasons. First, it could be that although AS0 can reach AS2, there's not routing connectivity between the part that it can reach and the other one. Actually, I don't think that makes any sense because it's the same subnet. So let's ignore that first bullet point. But the more important one, let me make a note to fix that, 36. The more important reason is one of policy. So just because AS1 has the ability to route to AS4 through AS2, it does not mean that AS2 will accept traffic from AS0 that is going to AS4. So AS2 has only told AS0 that it will accept traffic that goes to itself. So far, we don't know whether that information was missing on purpose. In other words, this could have been a secret that AS2 was keeping, that yes, it can reach AS4, but it doesn't want to tell AS0 because it doesn't want to be in the business of forwarding traffic in this particular direction for this particular source and this particular destination. It's perfectly within the rights of AS2 to keep those secrets, to give partial information if that's the policy it wants to enforce. And if AS0 ignores that and tries to do that inference and says, "Okay, AS2, you know what? You're playing hardball, but I know you can get there. You didn't tell me, but I know you can get there. So take this packet and deliver it." AS2 will just could just drop the packet and say, "I never told you that I could get there," and it would be right in that. So that the way BGP works is that advertisements have to be strictly obeyed. You cannot make inferences by combining 2 different advertisements. Okay. So let's review this let's consider a 7th AS joining, AS7, which has a different block of IP addresses, but it doesn't matter. It connects to AS0, and AS0 now has to make an advertisement to AS7 about what can be reached. Now, AS0 has 2 different ways to reach these gray ASs, right? It can either go down or right. Which should it choose? Why don't you think about that for a second? Well, it'll make a choice based on how potato routing, in particular, based on the position of this border gateway. So this border gateway that AS7 is going to be going through, this is going to be closer to either the next hop to the right or the next hop to the bottom. So if this is closer to the right, it'll go that way, the green one. If it's closer to the bottom, it'll go the red one. And that's important. I mean, you might not think it's important. You might think that I could abstract that, but it's important because the AS path has to be advertised correctly. So it'll either advertise 013 or it'll advertise 023, and that does make a difference to AS7, right? One of these 2. Although there's a way of looking at this where AS7 can aggregate this whole route into one rule as follows. Although this rule does not, you can't aggregate the different AS paths that are included if they're different. So I said before that it's not all about shortest path. There's also local preference. You can implement policies that force the hard code certain routing, often due to business considerations or knowledge you have about other technical things that aren't really captured in the hop count, like bandwidth limits and latencies. So AS0 has two choices here to reach this entire fake intranet. We could actually use local preference to subvert the shortest path that BGP will come up with and get the worst possible in terms of hop count choice, but you can do this with local preference if you wanted to. If these red lines were your local preference, for example, it would say that to get to AS2, which is the 1.2.0.0/16, you should go to 1 and then 3 and then 2. That's this second red one. Or to get to AS1, which is the first red one, you should actually go to 2, 3, and then 1 down. So kind of go around that way. That's like a longer one in terms of hop count, but again, that could be better because maybe, you could imagine a situation where this link to the right is really slow and weak and maybe costly, yet there's a really fast connection downward, and in these other two directions, these other two links could be superior in some sense to this other one. So that might be a reason why you'd want to use local preference to subvert the shortest hop count that BGP will give you. Final topic here, there are different types of autonomous systems based on the way that they use BGP and what they advertise. Okay, the simplest, and I have them drawn here in 3 different colors. So a stub autonomous system, this is maybe the simplest to understand and define, is an autonomous system that's connected to just one other autonomous system. So a stub autonomous system doesn't only advertises itself because that's the only thing it can route to. It's kind of like a client in some sense. That to abuse that term a little bit. A transit autonomous system is an internet service provider. It's like a part of the backbone. It has multiple connections and it will forward traffic between them. Okay, so and that's kind of like what I was showing so far in examples. Now, but a variation of that, just because you have multiple connections does not mean you're a transit AS. To be a transit AS, you have to be honest, I guess, or like complete in the advertisements you give. This multi-homed AS has multiple connections, but it has not made those connections for the purpose of helping others reach destinations. It's made those connections exclusively for its own benefit, to have fault tolerance perhaps, or to have increased bandwidth, and it only advertises its own IP addresses in its BGP advertisements. So technically, this multi-homed AS could tell this left purple one that it can reach the right purple one through it. In other words, to create a route that passes through it that way. But if it behaves, by definition, if it's behaving as a multi-homed AS, it will not do that. It will kind of keep that a secret and pretend that it'll do advertisements like a stub AS to both of these neighbors. Okay. So both the transit and multi-homed ASs have multiple connections, but they differ in their BGP advertisement policies, where the transit ASs give complete advertisements, the multi-homed ASs give advertisements only about their own IP addresses, so that they're not in the business of forwarding traffic that comes in and then leaves. Okay, the transit ASs do just that. They do that. So to reinforce this idea, what would happen to this network if this particular transit AS behaved as a multi-homed AS? In other words, it did not advertise the other destinations it could reach, but only advertised its own IP addresses as destinations. What would be the implication of that in this particular network? Well, it would be pretty serious, because if this AS stops forwarding traffic that goes in and leaves, then this internet would be broken in two, right? So the green ASs would only be able to reach this one other AS. They would not be able to reach the orange or the other purple one, because this purple one would not advertise its connectivity to those other ones, to the green ones. And the same thing in the other direction. So we would have how many different islands of internet here? We would have 3 islands of the internet. They would be overlapping in that they all could reach this one particular multi-homed OS, but then this would be an island, this would be an island, and this would be an island. They're kind of like a triple Venn diagram thing. Okay. To implement this, just to reinforce the idea, you have an AS that only advertises itself. So AS1 in this case, if it wants to behave like a multi-homed AS instead of transit, if it doesn't want to hand off traffic like from AS0 down to 3, it can just advertise its own subnet, and then even though it has the ability to reach these other ASs, these other IP address ranges, it will not advertise it. Okay. All right, so that was BGP. At first, we did a review of the distance vector algorithm. We showed how the count to infinity problem can lead to slow convergence when links get worse. The thing to remember there is good news travels quickly, bad news travels slowly. We have a solution to that through either poisoned reverses or by keeping a list of the path in the distance vectors, and BGP does that with the AS path. Routing on the internet is hierarchical, so at the highest level, the global level, we have BGP that decides the routes, but then at the lower level, we have interior gateway protocols that can be different in the different autonomous systems. Autonomous systems are grouped routers with one routing policy, so it's like a group of routers that are connected together that are managed by one entity. With interior gateway protocols, we can use link state algorithms, which is to say centralized algorithms like Dijkstra's algorithm, but with BGP across the whole internet at a global scale, we use a distance vector-like algorithm that's implemented with BGP advertisements as the distance vectors. It uses the shortest AS path hop count to find the shortest paths in the network. Of course, there also are ways to override this with local preference, and there are tie-breaking rules like that use hot potato routing. BGP advertisements have a IP address prefix as the destination, an AS path as the stand-in for the cost, and the next hop is expressed with the IP address of the router. That parentheses shouldn't be there. And when you make an advertisement, you're telling a neighbor not just that you can reach the destination, but that you're willing to forward packets from the person you're advertising to that destination. All right, that's it. Thanks for joining.